Welcome back. This is yet another day. I think it's a Tuesday, November 5th. Just an ordinary Tuesday, right? Nothing going on. All your intention, all your focus, right? We're all right here in class. That's right. Yeah. If something does go on today and it makes you somewhat anxious or otherwise apprehensive, you can always come back to Bayesian psychometrics. Always. They'll always be here for you. There's nothing controversial about it. Even if it goes wrong, it's still kind of innocent. It's no big deal. Okay? All right. Let's start by a couple announcements. Number one, no class live on Thursday. I have a medical appointment that I had to make. I broke my wrist a couple weeks, a year and a half ago, and I'm still having a little pain. So, unfortunately, I got to see a specialist, and that's going to happen right when we're supposed to have class. But that means after class today, I'm going to make a lecture. I'm going to finish this whole lecture on video, and I'll have a video for you to watch. So don't come to the Zoom room. You can just go to the YouTube and do that. It's right, the YouTube. I've officially reached that age where I put the in front of almost everything else. The YouTube exists on the internet, right? Yes, the online. Anyway, I can see old age coming, and I just have to sort of just recognize it. But so, what did I say? No class Thursday in person. There will be a video, and it will finish this. Second, related to class on Thursday, I have a new homework that I just assigned. This is basically taking homework number four. It's taking what you did in homework number three for the analysis, the CFA model, and converting it to a Polytomous IRT model using a graded response type model that we're going to talk about in class today, and we're going to talk about on the remainder of this lecture that I record last. This homework is due a week from Friday, so November 15th. Can't believe I still have 2022 there, even though this wasn't even 2022's homework. I thought I fixed it all because I fixed it up here. Evidently, attention to detail is not my strong suit. Anyway, it's due in the future in 2024 on November 15th, not on the past in 2022. And you should know that this will be, to me, I find this an interesting homework. I want you to think about this while you're doing it. Take a look at what you did last time with the CFA model, which is what we often use with Likert data, and compare the results to the IRT type model, which treats the data more appropriately as a categorical distribution. In particular, take a look at the distribution of the latent variables estimates, the EAP estimates, kind of compare and contrast them. That's a big difference between what we're doing when we assume the data are continuous and normal, which we probably shouldn't, and what we're doing with IRT or when we treat it as categorical. Okay, questions on any of this? All right, last bit of information is that I'm working on grading homework three and the intro to your project, and I'll have that done hopefully by the end of the week. So you'll be hearing from me on that very shortly too. Okay. All right. Let's get into the lecture then. This is lecture 4D. We are now modeling observed polytomous data. Polytomous is another word for multi-category. Sometimes we say categorical distribution, sometimes we say multinomial distribution, but polytomous is the big umbrella term for it. Often in an IRT course, you talk about binary data first and foremost and kind of get all the IRT concepts in, then you switch to what happens if there's more than two categories. That's what we're doing here. Um, I'm going to teach you how to do polytomous IRT or item factor analysis models, but I'm also talk about it more from a philosophical point of view, meaning what are the right distributions available for each of the items that we're talking about, each of the different variables. So it's going to start with a model that no one talks about, but just to make a point that we're trying to model data using the best distribution we can for it. And in a Bayesian sense, this is your choice, right? If you go to M plus, if you go to, I guess, M plus, you can sort of specify at the top which categorical variables, which count variables, and so forth, but it does it all for you. Go to Levon, you can specify which categorical variables are there. But in Bayes, you could build your own category if you want to, build your own distribution for it if you need to. So we're going to start with one just to sort of step that apart. Again, we're going to talk about conspiracy theories, which honestly, on a day like today, a normal Tuesday like today is a little bit. I'll bet today is Conspiracy Theory Tuesday. What do you think? Anyway, for those of you of English descent, it's also a very, very prominent day in English history, right? November, the 5th of November, the Guy Fawkes Day, right? So if you're not familiar with what that is, go and look up the 5th of November. You'll see a person in England tried to blow up Parliament. So that was good. You ever watch the movie V for Vendetta? That's sort of the mask is on that guy's face. So anyway, again, normal day, no worries about conspiracies, none of that stuff. Nobody would ever believe this crap anyway. So all right, but think of conspiracies. Let's think of the conspiracy that CFA has to say that all Likert data should follow a continuous distribution. Now, that's there's a conspiracy for you, right? This cabal of elite academics say that we should do factor analysis on a discrete variable. We're going to make it stop. God, I sound good at this. I better stop. All right. Why I mean that is we took a look at this data set, and you have a data set in your homework, the gambling research instrument data set, that had categorical response options, right? This Likert type scale. But in CFA, we conveniently forgot that they're categories, right? I don't know if you know you're really forgetting it, but the normal distribution says, nah, it's a continuous variable. So, a categorical response somewhere between strongly disagree and disagree might be appropriate, like a 1.25. That would be fine. That's different than a 1. But we don't have that data. You could think of creating a Likert style slider bar, and that would be good. Um, but we don't. So we have categorical data. So we should treat these data as categorical. So these are the questions again. This is the CFA model, right? This isn't good for data. We talked a little bit about that before, but remember, if we're going to impose a normal distribution on data, it needs to look symmetric. It needs to be continuous. Neither of those are likely true in our data, right? We have a whole lot of responses of absolutely not, I disagree with this statement. Can't be symmetric, right? The other thing that the CFA model did, this is an item characteristic curve. Remember, this is our latent trait, theta, the unobserved tendency to believe in conspiracy theories. And the blue dashed lines here represent the limits of the Likert item, right? So between 1 and 5 are each of those responses. The red dashed line is our EAP, expected score for a given value of theta. And you'll see quickly a little over a half a standard deviation below 0, below the mean, we start saying the expected score can't be possible, right? Another way of putting it is these people down here, they couldn't disagree more. I guess you could say that. But that's not a good thing in statistics, right? When your model comes back and says, yeah, I predict things that aren't possible, that's an indicator that something is amiss. Okay? So what do we do to fix it? We need to change our distributional assumption. Now, remember, in this generalized latent variable framework, right, where we say, I sort of described, data on the left-hand side and model on the right-hand side. In this case, what that means is our model or our theory on the right-hand side isn't changing. Again, our data now is different. So we need a distribution that maps our theory onto our data. And so that's where Polytomous data distributions show up. What we need is our observed data. What we have in our observed data are discrete responses, a small set of known categories, 1, 2, 3, 4, 5. And we saw that some item response distributions, if we just look at the marginal distribution of responses, they may be multimodal, right? Meaning that you may have a bunch of people who said strongly disagree and maybe people who are somewhere in between. So a shape of a distribution that has more than one peak to it. That again is important because again, if you're pretending the CFA model approximates your data approximate a normal distribution, you will need it to be symmetric. Ours aren't. And it's unimodal, like one big peak, and symmetric. Ours aren't that way. So our choice of distribution must match our data, right? So that means it needs to be capable of modeling a small set of known categories, right? I mentioned this again, small set of known categories, right? And I say it that way because if you think of a different way of asking a question, right? Or if you think of a different type of category, we could have basically potentially an infinite set of categories. If you think of a discrete variable, a count variable, how many times, did you breathe today? How many times did your heart beat today? Or, Like these are counts that can have discrete numbers, right? So they're not fully continuous, they're a discrete sample space, but the sample effectively goes to infinity or quite large. This is different, right? There can only be one of five numbers. So the small set of known categories tells us one set of distributions or family of distributions to use. Whereas if we had infinite discrete data, that would be a different set, right? So when I say these sets, the small set of distributions we're going to talk about today, the infinite sets we won't talk about, probably don't have time for this class, but things like Poisson distribution, a negative binomial distribution works with counts. With count data, both of those have certain assumptions that go along, particularly with Poisson. The mean and the variance are equal, assumed to be equal, and often that's not the case in data, so you may have to adjust it. Sometimes use the negative, excuse me, a zero inflated Poisson, sometimes called a hurdle model. There's all sorts of ways to have to deal with extra zeros, but we're going to cut that off right now. The same premise applies. For us, we're going to talk about finite numbers of distribution, finite numbers of categories. Um, so we need a discrete distribution with a limited number of categories. I say a fixed upper bound, right? It's different than a count where the upper bound could be infinity. We have one, two, three, four, five. And this distribution needs to work with multimodality potentially as well too, right? So we need to have a distribution that might mold itself to different shapes. Remember last time when we talked about the beta distribution, it was the prior for our C parameter. You could have weird shapes in beta, almost like multiple modes. You could have a U-shaped even, right? Where the modes are at 1 and 0. We need that, basically. How are we doing so far? Get the thumb meter here. Okay. So what are these discrete data distributions? Turns out there's a ton of them available in Stan. Now, we're not going to use all of them, but you could. Literally, in this idea of a factor analysis, in the generalized latent variable model, you could come up with you could have data that follow any of these right here. So if you wanted to see that list of discrete distributions, here they are. Right? We've got binomial, got, I'll just go down back to my slide. I summarized it a little bit better. Long story short, there's a link to the Stan user manual. You can see the functions for it, but let's talk a few about it. There's a binomial distribution, right? It's an extension of the Bernoulli. A Bernoulli is actually one trial binomial, right? The pro for that is it's really easy to use in code. In fact, very little changes. You just decide to call it a different distribution. The con for it, the downside is it's unimodal. Binomial distributions want one peak. So probably not going to fit our data well. But that's a topic that we'll cover soon as well, too. There's something called the beta binomial distribution, which often isn't used in psychometrics, but it generalizes a binomial distribution to have a different probability for each trial. Basically, it's the idea that in a binomial distribution, we have a parameter that represents the probability of a success on any trial, right? Which we have to sort of think about what that means. But that's like the probability of a one in a Bernoulli. The binomial just takes that up at the same probability. The beta binomial puts a beta distribution prior on that probability, which is desirable because it does shift the mean and variance a bit of the regular binomial. So if you have a binomial where the variance is not quite what the data maps onto, beta binomial may work well. We don't see it a lot in psychometrics, but it could be there. There's also a hypergeometric distribution. What's that? But you could use it. Hypergeometric distribution, if you take a distributions course in the Department of Statistics, you will see it associated with the probabilities associated with drawing multiple, like if you have a big, they always talk about an urn full of ping pong balls, and there's white, yellow, green. What's the probability of picking three white and from this urn simultaneously? If you draw three, that's a hypergeometric distribution for you, right? Um, but finally, the categorical distribution is really what we're going to be focused on, sometimes called a multinomial distribution. It's our base distribution for if you've taken an IRT class, these are models that you probably have heard before: greater response models, partial credit models, and nominal response models all are subsumed into this categorical or multinomial distribution. So when we talk about these different types of models, that's different ways of parameterizing the probability a person answers with a given category conditional on their latent trait or traits, right? So we're going to dwell most of our time in categorical. And then there's this other one called the discrete range distribution, which I would call a discrete uniform distribution, which says each one of these categories is equally likely. Yeah, if you have that, you could use that for data. However, it's not really that useful because it doesn't really contain. If every category is equally likely, what are you going to do? You're not going to get much information about your latent variable out of it, right? So anyway, those are the discrete data distributions in Stan. And again, I'm going to make the point. I'm covering today. I'm actually going to show you binomial first because it's an easy step forward, and then I'm going to get into categorical distributions. But literally, every one of these you could use in a psychometric context, right? If you wanted to, or if you had a motivation to. All right, let's talk about binomial distribution models to begin with, shall we? Actually, can you give me just one moment? Actually, no, I think I'm okay. All right, here we are. Binomial distribution models. The easiest, most straightforward extension to get to a Polytomous model. Basically, the idea is this. We have the binomial distribution is a distribution describing the probability of the number of successes out of the number of trials. So think of let's set up the binomial distribution as you may have heard about it in introductory statistics. Let's imagine um, I'm going to roll a die, and or actually, yes, I'm going to flip a coin. Let's do that, right? And I'm going to count the number of heads, right? So y is going to be the number of heads I flip. I actually flip, and n is the number of times I flip the coin. So what we're looking for is the probability of I observed, 5 hit heads when I flip the coin 10 times, right? So this is what the distribution is for. So here, this n over y in parentheses is referred to as a combination. N choose y, the number of times that we can choose, 5 heads out of 10 trials. So if you think of it this way, each of those 10 trials is a 0 or 1, right? There's actually 1,024 versions of patterns of 0 or 1. What number of those 1,024 have exactly 5 ones in it? That's what this is telling you, right? And then uh, that number is multiplied by the probability for any one trial of observing a head, right? So in our case, um, that'd be zero point 0.5 on a fair coin. Remember, typo on the slide. Hang on, let me make a note. Slide 10, gotta fix this, but K, this actually should be Y. P, the probability of any one heads, is raised to the number of heads you observed. And then 1 minus P is raised to the number of heads you didn't observe. So 1 minus P is the probability you flipped a tail. And N minus, in this case, K should be Y. N minus Y represents the number of times you flip tails. Right? So it's a very simple, straightforward model. And why I like it is you'll note there's still one probability, right? So when you use this model, a couple things come from it. Number one, the mean of this distribution is n times p. So basically, in our case, I mentioned a coin flip. If we have a fair coin and it's 50-50 to flip a heads, the mean number of heads will be zero point 0.5 times the number of coin flips, or 10, which we would expect, 5. The variance, once we know the mean, just like the the Bernoulli distribution, we know the variance, right? The variance is n times p times 1 minus p, right? So p of 0.5, again, is the highest level of variance, right? Results in a variance of 10 times p times 1 minus p, or 10 times 0.25, or 2.5. So our variance in this case is 2.5. So if we want to put that into more useful terms, if we flip the coin 10 times, it's heads, and we would expect 5 heads on average. But if we took the square root of 2.5, we would see what the standard deviation happens to be. There will be some wiggle room out of that. Cool? So, question for you. How on earth can we flip a binomial model into something we can use for Likert data? Hmm. Are those Likert scores um, trials? Exactly. You can think of the number that a person selects on a Likert scale as the number of successes, if you want to think about that, right? And one way Ryan mentioned, which was great, which is if you really wanted to think about it, if we have the numbers 1, 2, 3, 4, 5, right? We could take a person's data. Let's imagine someone picked a 3, right? Well, if we created 5, 0, 1 variables, a 3 would have to have 3 ones, right? Where the 5 represents the sum of those 0, 1 binary variables. That's one way of thinking about it. When I first accidentally stumbled on the binomial distribution, I used to call that the pseudo item distribution. This is 20 years ago. Ironically, in summer, I think it was when I went to Prague for IMPS, there was someone presenting on this in a different part of, actually, no, it was Seoul, sorry, World Tour this year, Template's World Tour. Back in Korea at the conference there, someone was presenting on using this pseudo item approach to transform machine learning models into estimation because a lot of machine learning methods that had been built had been using binary data but not discrete categories. So it was an interesting way of doing it. Anyway, for us, we have to believe the following, right? Here, let's talk about it a little bit. Although it doesn't seem likely that our items fit with the binomial, we can actually use the distribution. As Ryan had suggested, as I mentioned, if we think about it this way, we have the categories 1, 2, 3, 4, 5. We had before called them numbers 1, 2, 3, 4, 5. There's nothing magical about 1, 2, 3, 4, 5. We don't have to call them, you know, integer values, but we could actually shift the scale just slightly and move the lowest value to 0. Really, our categories are 0, 1, 2, 3, 4. When we do that, now it looks like everybody's score is the number of quote unquote successes out of the number of trials, right? So that person with a 3, when we subtract 1 from it, there's 2, value of 2 for him or him or her, right? And so therefore, um, that set of data um, would fit this distribution. We just have to subtract 1. We have to make sure the lowest category is 0. And we have to make sure that we know that the highest category, in this case, when we subtract 1 from it, the highest category is 4. That's the number of trials for everybody. How's that sound? So we let number 4 be the number of trials for everybody, and their score minus 1 being the number of successes. We now have a psychometric model that fits binomial. So now we have to map that probability of each item's success onto a latent trait. We know it's a probability. In fact, we can use the same item response function that we used in the 2-parameter logistic model, right? We could use a slope intercept form where we take the probability. We use an inverse, in this case, the probability is equal to an inverse logistic link function, where our linear predictor, our psychometric model itself, there's another typo, slide 11, our psychometric model itself is contained in the exponent, right? So we have a latent variable. We call this a factor loading or a discrimination parameter, and we have an item intercept, right? Similarly, just like we could with all the IRT, the binary IRT models, we could have used a probit link function here. We could have used a log-log link. We could use any link function that works with the Bernoulli. We could also parameterize this as discrimination difficulty instead of slope intercept. Heck, we could even include lower or upper asymptote parameters. We can include a C parameter or a D parameter if we wanted to. So really, um, the Bernoulli model, the distribution that we saw last week, is still at play here. It's just now a binomial, right? So generalized Bernoulli, if you want to call it that. Questions on any of this? Anybody? I take that as a no. Okay. So what does the model itself look like? This is the likelihood. This is the PDF. Because binomial is discrete, we sometimes call the PDF the probability mass function, PMF. That's the same idea. The probability a person gives a given response conditional on their latent variable value is the Bernoulli, or excuse me, the binomial distribution PDF, right, that we saw before. But here, n is the number of possible options, right? The highest number. I guess this is our number of trials. So highest Likert number minus one for us, so number four. Y is the score minus one, right? So it's the number of successes. And the probability is now replaced with our psychometric model. So for each item will have its own intercept, its own discrimination parameter, and there's yet another runaway parenthesis. So 3 slides in a row with typos. Way to go. Killing it today on this normal Tuesday. Um, there we have it. So basically that probability is replaced by our item response model in each part. And now we can estimate this, right? Anybody ever seen a binomial item response model before? No. There was a paper. So again, I mentioned that I actually stumbled upon this. I think it was during I was working in grad school on my dissertation work. Um, and there was a paper by, I can't remember the first author's name. When her friends say her first name was Judy, and then the second author was Terry Ackerman, who used to work here at Iowa. And they had a paper in the 80s that sort of showed this as well. I thought it was pretty cool. But other thing to note here, all right, is that unlike any of the other models we're about to get to in this lecture, the binomial item response model is awesome because it does not include any additional parameters from the IRT two-parameter model. All the other models that we're going to get to start to have lots and lots of parameters per category. And as you can imagine, even though Bayes is amazing and prior distributions are our best friends, it can be very difficult to have estimate models with lots of parameters for categorical data because you may just have very low counts in certain categories, which cause the parameters to go crazy. Some of the parameters to go crazy. That's not going to be an issue in the binomial. The binomial almost always works. So it's a good, basic, probably incorrect, but a little bit more correct model than CFA. All right. So we can use the same prior as before, our normal prior and our for each parameter. Likewise, we can identify the scale of the latent variable. We're going to use a standardized factor here. So how do we estimate it? In Stan, let's start with the model. Here we're going to say y follows a binomial distribution, right? The binomial distribution in Stan, and I close the Stan syntax. Let me do that real quick here. And when we go into the user guide, I should probably start showing you how to use the user guide because it is your breadcrumbs for figuring things out. That basically, when you say something follows a binomial distribution, it's looking for n, which in this case is the number of trials. And I put that in quotes with my fingers on this camera, but you won't see that on YouTube. The number of trials for us is the maximum number of categories minus one, right? So our top Likert score 5 minus one, which makes it 4. And then theta, it describes, if you have to go back to this PDF or PMF looking function, theta is in the spot where the probability is. So we know that n has to be the top number for us. In our case, every item will be 4 for n, but theta is the probability. So that's where we have to take our inverse logit and put our psychometric model. So let's do that, right? So we got binomial. Here, max item is what I'm calling the top category, the number of trials for each of the items we have. So again, each item we have used to have numbers 1 to 5. That means if we subtract 1 from every one of that, max item for each item will be 4. I'm doing it this way because you may not always have the same number of categories in each of your items, and that doesn't have to be the same across the assessment, across the data that you've collected, right? And then where the probability goes, you're familiar with this. based on the end of the IRT lecture, the inverse logit function is applied to mu plus lambda times theta for this mu for this item, lambda for this item, theta overall for the person. So this is the same form of the model that we saw with the latter part of the IRT lecture. How are we doing? Pretty good so far? Okay. Yes, Vladimir. That's right. Yep. Hmm? Yes. Great question. The question was, is this like CFA but with limits? It's actually not. And here's the reason why. Sorry. This distribution is again approximation, and in that sense, it's like CFA. The binomial distribution will be a symmetric distribution. Okay, so that's the one uh, similarity of CFA. However, when you look at the distribution function, the probability mass function, this is only defined for discrete outcomes, whereas CFA assumes that we collected data there 1, 2, 3, 4, 5. In CFA, we say, no, 1, 2, 3, 4, 5. Yes, even though we collected those, any number is possible. It's a normal distribution, right? We just happen to observe just the integers between 1 and 5. What the binomial is saying is, no, there is no such thing as a continuous integer, a continuous number. We have, in this case, 5 numbers allowed, and that's 0, 1, 2, 3, 4. And so we have to map our 1, 2, 3, 4, 5 into 0, 1, 2, 3, 4. That's all. Does that make sense? Turns out I am using a link function. I am using the inverse link function. It's just I have to put it in the probability spot. But yes. So for discrete data, you will always have. This is a great question. Um, in pretty much every possible non-normal model you have, you will likely have a link function involved with it. There are some well-defined cases where they're not, but usually you don't see those in psychometrics, or they're in weird psychometrics like what I do, which is diagnostic. Well, used to do diagnostic models. There's several crazy models that are identity linked. You don't want to use those though. So the bigger picture is because the probability when we look at this distribution function right here, right? Basically we have to go and say where can we number one adapt our data to it, and that's we just need to be on the range from 0 up to 4 instead of 1 to 5. That's the data part. And then number two, we see that the parameter theta, again, this is math language, but I'm going to decipher it here. It exists between 0 and 1. And so because of that, the way that I look at this, I say, okay, so number one, just subtract 1 for all my data. Number two, oh, that's bounded. I need to go and unbound it. So what do? I look for my link functions that map a 0 to 1 parameter onto the real number line. And of that case, inverse logit is there. Does that answer your question? Thank you. And so actually this is a good point. Why am I going overboard on a model that nobody uses? It's the concept, right? I want you to be able to think outside of the box when it comes to psychometrics and not manipulate your data to fit an existing model, but to create a model that fits your data the best you can. And in that case, the search for different distributions for data is part of it. And I'm leading with that because when I use Bayes, it's usually for a model that I can't get working in other packages. So I have to be somewhat creative. I have to learn about that for what I do. Actually, that's not true. I use Bayes for everything. I use Bayes to write my grocery list, for heaven's sake. It's cool. Stan can't quite get there, but that's where Jags comes in. All right, enough dad jokes. Let's think of it this way, though. I'm talking about this for the concept of generalized modeling. It fits really well. I picked a distribution. I see how I can adapt my data to it. Turns out that adaptation doesn't change anything about my data. And then I need something to do to parameterize what's the mean, basically, and apply a link function to the mean for it. And speaking of my data, right, we're used to data being stored as discrete. Like if I go to my RStudio window, oh, my little laptop's overheating. But we are used to these Likert values, 1, 2, 3, 4, 5. But do they have to be 1, 2, 3, 4, 5? No. Even though everybody in the world with a Likert scale starts with 1 and uses integers up to some number, they didn't have to do that. That's just by convention. Those are arbitrarily assigned numbers. The key that we have to remember is that the value of 1 represents less agreement than the value of 2, right? That's it. They're sort of ordinal measures. So us subtracting 1 and making the range 0 to 4 to fit our distribution doesn't really, it's a transformation of our data, but it didn't change any of the meaning at all. It just moves it down 1. It's an arbitrary shift. Very much like if in analysis of variance, if you choose the dummy code or reference code versus if you choose to affect code, right? The category, you're coding up what your categorical predictor should be with zeros and ones in one case, -1 and 1 in another, but the result is the same. Same with us here. Cool? So sorry to go overboard on that, but I'm really glad that you asked that question to help me sort of describe motivation here. So, any other questions on this before I jump back in? Okay. So here, the key thinking here, the only thing difference between this slide and the end of the IRT lecture when I had Bernoulli is this name binomial, right? I chose a binomial distribution as a function, so therefore I had to put a new parameter in, max number of trials, but the rest of it looks like the same. Before it was Bernoulli, and it had the inverse logit to it, right? So that's cool. Turns out our priors are the same too. Theta has a standard normal prior. We can use the same multi-normal prior on lambda and mu. And the other thing we have to think about is the data type. Again, Stan here tells you a bit of that. Um, doesn't quite tell you here. Oh, there it is. Yes. You have to sort of decipher Stan E's to figure this out. This Stanlish, is that it? English for Stan? Probably not. And of course, I don't see it up here. But basically, what I wanted to see is it telling me what type of data show up here. Turns out you can't really define it. It doesn't really say it here, but below you see that integer is an n and a real number is theta. So for us, what we have to note is y itself has to be an integer. Remember that that's the type we had for IRT. And then max item, the range 0 through max item has to be encoded in y. So again, the parameters block is the same, no changes from before. And the model data block turns out to be the same also, with the exception of we need the max item, right? The total, like the number of trials, right? In this case, it'll be number 4 for each of what our items are. All right. Questions on any of this? This is where Bayes starts to look like a cooking show. All right, now I have all this code. I'm going to go stick it in the oven and see what happens. Actually, not quite yet. Almost there. Preparing our data. If we were to prepare our data for Stan, first of all, we need to subtract 1 from each one of our items. That's what I do here. Bernoulli items construes the items binomial. And if this cooperates, I can show you it. Let's try that one. There it is. Right. So now our range of items goes from 0 up to 4. And then there's our check for it. Our max item just takes each of those items and asks for the maximum, right? So the category is 4. All right. I will note there is a little bit of a flaw with this right here. Anybody want to guess what that flaw might be? If I wanted to give it the number of trials in this syntax, see, I'm already picking on my own code. For those of you who have me on your dissertation committee or happen to be helping you with your dissertation, this is the experience you get. I will be critical about everything, even the stuff I write. But that being said, what's wrong with this? What happens if we have an item where nobody predicted or said strongly agree? It doesn't have the same range. We just didn't observe anybody there. So this code assumes at least one person answered with the highest category for each item. That's probably, I should probably hard code that, right? Because even though nobody responded there, the binomial distribution can map to that probability very easily. All right. So how do we call Stan? The same way we did before. I still have my initialization for theta here. I did put that back in this lecture. And I initialize lambda to be positive. We still have to worry about initialization to make sure that we don't have bimodality in our posterior, artificial bimodality. And then we just run a chain, and here's what we get. All right, look at this. Did we converge? That's some good convergence right there. That's what I want to see. Binomial is one of the better behaved distributions. It's very easy to get things to converge in it, just like normal. After that, you're on your own. Good luck with the rest. Here are our parameter values. Turns out we interpret those the same way we did before, right? So this is the increase in the log odds of the probability of a success now in a trial for every 1 unit increase in theta. Mu represents the expected log odds of the probability of a success when theta equals 0. But now we can come up with something cooler. This is what we call the option characteristic curve. Remember in IRT we had the item characteristic curve, which mapped the expected probability of a correct response onto the theta axis, right? So you would, like this blue line is what we had seen before. Well, it turns out the item characteristic curve, when we only have two options, we never draw the complement, right? The second curve. But when we have categorical data, we can draw basically an item characteristic curve for each of the categories. And that's what you see here. And how we read this is basically thinking about, again, the y-axis is theta. The x-axis is theta. The y-axis is the probability that option is selected. And each option, 1, 2, 3, 4, 5, and now let's remember, option 1 is strongly disagree. Option 2 is slightly disagree. Option 3 is neither agree nor disagree, and so on, right? So remember each of those options there. So if we're going to look at this, what we do the following. We'd say, okay, what is for any given value of theta, what's the most likely option picked? Right? And you can see this black line is strongly disagree. It's far above all the other lines up until you get to a little below 1 standard deviation above the mean, right? So basically, you have to be a little below 1 standard deviation above the mean on our latent trait to even to have a fair chance of picking one of the other options for the item. The other thing I'm going to note with this is if you take a slice, let's say the value of theta equals 1, and if you sum up each of the different points of those lines, it's going to sum to 1, right? So this is complementary, right? Each one of these is our probability distribution. It's formed by the binomial itself, right? So now what we can say is, okay, I like to think of ranges of theta where people will respond, right? So negative infinity all the way up to about 1 standard deviation below the mean, people are saying strongly disagree. Then we have a narrow window just right around 1 standard deviation where people say slightly disagree. The people who are neither agree nor disagree are somewhere between 1 and 1 1/4 standard deviations away. And then slightly agree goes a little bit further, 1 1/4 up to maybe 1 1/2 standard deviations. And then everybody who's over 1 1/2 standard deviations from the mean, above the mean, has a better chance of saying strongly agree, right? But even that better chance, there's still a good chance they say slightly agree or neither agree nor disagree, right? But that's our option characteristic curve. Any questions on this curve? You want to see how to draw it real quick? Because I like these pictures. You might like them too. How we draw that plot is here in my code. Of course, you can sift through terrible syntax, but I grab our mu, I grab our item parameters, and basically I calculate the probability of a correct response for each, and that is using, let's see here, item summary. Oh, this is my CFA model. No wonder. I don't see my binomial distribution. Here it is. R has a built-in function for the distribution of the binomial, basically. So the y-axis that you saw is taken from me putting each of our EAP estimates into our item, and EAP estimates of mu and lambda, and then any value of theta, converting that to a probability and asking for the distribution function for it. Okay, let's keep moving forward. So option characteristic curve is the probability of selecting each option in an item, right? Conditional on theta. Item characteristic curve is the expected response value for the item. Now, you would think they mean the same thing, but they're not quite the same when you get to polytomous data. In binary data, they are the same thing, although we omit the incorrect option from our option characteristic curve plot. But think of it this way. If I were to go and map our data back onto the 1 to 5 scale, right, I just have to add 1 to each of the predicted values from before, our item response model gives us the probability any one person, you know, has a different score, right? But we know what the mean is. In fact, we go back in time here, we know in the binomial distribution, the mean is n times p. And the mean is our expected response for an item. So what we do is we figure out a person's probability of answering a success, right? We have their theta, we have an item's mu and an item's lambda, right? And we put that in the inverse logit link function. We get probability out of that. And then we multiply that by n, which is the number of trials. In our case, that's 4, right? But we know that we had to subtract 1 to get to the range of our data, so I just did n4 times each person's probability p plus 1. And so that turned out to be this plot, the item characteristic curve. And what you see here is on the y-axis is our expected score on the item in our original Likert score range, right? Now remember, an expected score is a mean. It's not a discrete score. It's what our numeric value we expect to happen, right? Just like in a binary variable, a 0 and 1, the mean is the number in between the 0 and the 1, right? For us, the mean is the number between 1 and 5. So again, we can see the expected value a person's rating would be on the item for a given value of theta. And here, where our expectation, you can again see something very similar to what we saw in our previous plot. Our expectation is basically the lowest response category up until a person's theta is about 0. Then it starts to slowly ascend and then finally moves up to the top by 3. But I show you this plot because I want to compare and contrast this with the confirmatory factor analysis plot. Remember the CFA plot was a straight line number 1, and we were out of bounds before. But what the binomial distribution has done is it allows us to basically keep predictions in bound, keep our mean in bound, and fit our data a bit better, I think. Questions on any of this? What do you think of binomial? By the way, there is no name for this model. It's not binomial IRT or BERT or, I don't even know what you call it. For binomial item factor analysis, BIFA? I like that one. We'll call it BIFA. That's the BIFA model. Yeah, I fit a BIFA model. Now you sound much more intelligent when you put an acronym. right? Never mind that the letters for the acronym can mean nothing important, right? All right. Now let's take a look at our latent variable estimates. This is our EAP estimate of theta again, histogram of it. We can look at our latent variable posterior distribution. Notable about this is that the shape is slightly wider in cases versus others. And this is exactly what we saw in IRT. Remember, in IRT, the posterior standard deviation depends on the size of the posterior standard deviation depends on the value of the latent trait. Right? So here, theta 1 is the pink distribution. It's a bit wider of a standard deviation than theta, the second theta. And you can see if we plotted the EAP mean of theta by its standard deviation, you can see how that looks as well. Again, a nice curved plot like we'd expect. So what we've actually, there we go. Also, if we wanted to compare our EAP estimate of our latent variable with the sum score, we would also have a nice ogive looking function, right? Nonlinear. How are we doing? Now, would you like to compare the thetas? This is the part I was telling you about homework. Although I asked you to do a graded responses to our next model. The theta EAP estimates are next here. And this is kind of funny. This is our binomial theta. This is our normal theta. The range isn't all that different. I mean, it's slightly different, right? Um, Normal theta ends at -1, whereas binomial theta goes a little bit lower. But these are different metrics of theta altogether. And not only that, you can see a nonlinear relationship, right? CFA is completely linear, normal. We didn't put a link function into it. Whereas binomial has a link function. It's nonlinear, basically, right? All right. How are we doing? Hanging in there? Questions on any of this? All right. I got 15 minutes. Let's see what I can get to. That's binomial. I like binomial, but I don't think it's going to fit for our data. Do you? Probably not. Let's talk about a little bit more general model. This is a categorical or a multinomial distribution model. The multinomial distribution, the word nomial shows up in it. It shows up in binomial. You can think of it as this a multi-category distribution where in binomial, the reason why it's bi, well, there's bi meaning like the Greek, I think it's Greek for two, right? Is because for every trial you could either have a success or failure. In a multinomial distribution, for every quote unquote trial, you can have multiple categories that you could land in. Instead of just having two that we artificially called success or failure, in a multinomial distribution, you could have one, two, three, four, five. That'd make a difference. None of these are called a success. None of them are called a failure. But basically, what it turns out to be is this multinomial distribution is specified by, and let's ignore this crazy constant in the front. Sometimes we call this a normalizing constant. Ignore that for just a moment. Think of it this way. In the success versus fail, the number of trials versus number of successes, like binomial, let's hold on to the number of trials, right? Let's imagine I have a six-sided die. There we go, right? And I want to roll the die 10 times, right? But instead of counting a success as the number of times I've rolled a one, here I'm just going to count the number of times I rolled each side of the die. Does that make sense? Right. So in a multinomial sense, the number of trials would be n as well, and y would represent the number of times that head or that side of the die was face up. Right. So in a six-sided die, I would have six different categories. Right. So what the multinomial does is it says each category has its own probability of occurring, and the probability mass function, or the PDF, if you want to call it that, takes that probability and raises it to the number of times I observe that die being that face up or down. Right. So this is basically the idea. Remember, if you didn't observe any in a category, that's a zero. Raising a probability up to a zero um, becomes a one, so not a big deal. And then this normalizing constant right here, when you see this exclamation point, you need to say the letter really loud. N. No, I'm just kidding. What that really means is factorial. And if you remember, I believe Algebra 2 is probably where I saw that. By the way, I got a big fat F in Algebra 2 in 10th grade. So if you're like me, a little refresher. That just basically means multiply all of the integers from the one before it all the way down to 1 together. So n factorial means n times n minus 1 times n minus 2 dot dot dot. Right? So here, what this term in the front does is basically normalizes the distribution so that the probability mass sums to 1. How are we doing so far? Okay. Now, how do we adapt the multinomial distribution for item response models? It turns out each item is a single trial. So n is always 1. So if you look at this distribution, when n is 1, all of this goes away because 1 factorial is 1. Turns out a 0 factorial is also 1, which seems like cheating, but it is. It's 1, right? And so you'll have 1 in the numerator, factorial. You'll have all the y's being 0, with the exception of 1, potentially being a 1. So there's no way that this normalizing constant can stay present at all. So oftentimes, when n equals 1, when we have a single trial, this distribution's name becomes categorical, right? So a categorical distribution means a one-trial multinomial, just like a Bernoulli distribution means a one-trial binomial. Cool? Yes, I think it's cool. No, never mind. You're cool. I don't know if this is cool, but you're cool, and I'm good. We're good? We're good. All right, never mind. Foot in the mouth again. Come on, Templin. All right. So what we do is we say there's one trial. And then what we basically say is the probability that a person answers with a given category is simply equal to the product of all the categories that we have raised to whether or not that person use that category. This I function, sometimes called an Iverson bracket, sometimes called like an indicator function, just means that the thing in the bracket is true, it takes a value of 1, and if it's not true, it takes a value of 0. So literally, our model is just that probability itself raised to whether or not the item response happened or not. Pretty cool, right? So now we're starting to see the setup. And just like you saw before in binary land and in binomial land, we have probability, right? So you're probably thinking, I know what to do. I can take that probability, apply a link function to it, put my model in the link function. Are you thinking that? I hope you're thinking that. That's a big part of what I'm hoping to you think here. But it's not quite that easy because we don't just have one probability, we have a probability for every class, for every category. Now, it's a little bit more simple than that because all of our probabilities have to sum to 1. So what that means is we can only model the number of categories minus 1 because this last probability can simply be 1 minus the probability of all the sum of the probabilities of the other classes because they sum to 1, right? So that's the one catch to it. But if we have multiple probabilities, how do we handle that? Turns out we put a model on that expands the number of parameters to fit. So basically, each one of those probabilities we have to do some type of model with. That model has to look familiar across each of the probabilities. Uh, and there's many different choices for how you can choose a model there. Okay? One of the choices is called a graded response model. The graded response model, sometimes called an proportional odds model, um, treats those probabilities as being basically ordinal. The categories is basically being ordinal. Um, we allow for an item response looking model for each of the probabilities where theta times the factor loading is the same for each, or theta times item discrimination, whatever language you want to use, but the item intercept changes for each category. So each category may have its own intercept. And sometimes we call these category response models themselves, or submodels, as Lisa Hoffman is fond of saying. I keep referring to Lisa Hoffman. I should do a collab with her on YouTube. That would be great, wouldn't it? Yeah, especially. All right. Um, so this is called a proportional odds model because the odds of picking each category are proportional once you condition on a value of theta. And I'll show that in just a bit. Um, there are other versions of this as well. One is called a partial credit model, right? So now in the proportional odds or the greater response model, the other thing I forgot to mention is even though there's a different intercept for each category, they are in order because of the idea of sort of our responses looking like ordinal data, right? Meaning a response of one indicates less agreement than a response of two. To model that, that means for a given value of theta, the probability of one should be, commensurate with the probability of two and so forth. So what we end up having here is changing our intercept. So each intercept gets ordered in this model. The partial credit model is where we allow for unordered item difficulty parameters. And then the nominal response model, sometimes called the generalized logit model in categorical data analysis, allows for an unordered set of intercepts and an unordered set of loadings. Yes, that's right. So each submodel has its own intercept and its own loading itself. How's that working so far? Everything okay? Questions? Okay. So the other note I will tell you is the term greater response model, partial credit model, and nominal response model came from educational measurement, right? Those were developed in educational measurement, but they mirror models that were developed in categorical statistics, right? Proportional odds, generalized logit, although partial credit doesn't really have an analog, I don't think.